Had is to select 6 cookies from a tray containing only chocolate chip, oatmeal, and peanut butter cookies. There are at least 6 of each of these 3 kinds of cookies on the tray. How many different assortments of these 6 cookies can be selected? So this one is basically just the equation A plus B plus C is equal to 6, where A and B and C are greater than or equal to 0. So this is basically stars and bars, or you can just count it because 6 is a pretty small number. So using stars and bars, we just get 6 plus 3 minus 1, 3 minus 1, which is equal to 28. Problem 2. Jacob uses the following procedure to write down a sequence of numbers. First, he chooses the first term to be 6. To generate each succeeding term, he flips a fair coin. If it comes up heads, then he doubles the previous term and subtracts 1. And if it comes up tails, he takes half of the previous term and subtracts 1. What is the probability that the 4th term in Jacob's sequence is an integer? So basically, we're just going to make a tree of all possible sequences he could take. So from 6, heads gives him 11 and tails gives him 2. From 11, a heads is going to give him 21 and a tails is going to give him 4.5. From 2, a heads is going to give him 3, and from 2, tails is going to get him 0. So we're just going to check this one more time. Firstly, notice that if he comes up heads, then it's going to be an integer no matter what. So there's a half chance of him getting head on his last turn. And what if it comes up tails? The only way it can be an integer if it comes up tails is 0, which brings it to -1. 3 gives 0.5, not an integer. 4.5 gives 1.25, not an integer. And 21 gives 9.5, not an integer. So the other case is only one possible sequence out of 2 cubed or 1/8. So the total probability is 5. Okay, problem 3 is 2 cubical dice each have removable numbers 1 through 6. The 12 numbers on the 2 dice are removed, put into a bag, and then drawn one at a time and randomly reattached to the faces of the cube with one number to each face. The dice are then rolled and the numbers on the 2 top faces are added. What is the probability that the sum is 7? Okay, so this problem might look annoying, but there's a trick that you can use to solve it. So basically, consider that every number is a different color. So if we think about it this way, it's easy to see that any combination of 2 of these numbers is equally likely to come up. So we have to divide the total number of possible combinations of 2 of the tiles and the sum and the number of which that sum up to 7. So let's find the number of them that sum up to 7. So it can be 1 plus 6, 2 plus 5, or 3 plus 4. All of these have 4 ways. 1 plus 6 is this one and this 6, this one and this 6, this one and this 6, or this one and this 6, which has 4 ways. Both of them also have 4, but basically the exact same combinations. So 4 plus 4 plus 4 is 12. And in the bottom, we have to put the number of ways to choose 2 of them. which is 12 pick 2. And this is equal to 2 11ths. So our answer is D. Okay, problem 4. 8 people are sitting around a circular table, each folding a fair coin. All 8 people flip their coins, and those who flip heads stand, while those who flip tails remain seated. What's the probability that no 2 adjacent people will stand? So basically, we're going to find the number of possibilities and then just divide it by 2 to the 8 equals 256. So there are 5 cases. 0, 0, head, 1, head, 2, head, 3 head is a little more complicated. I'll put 4 head on the other side. And we're going to count the number of possible ways that no 2 people who flip heads are next to each other in each of these possibilities. So if no one flipped heads, then obviously no 2 people flip heads will sit next to each other, and there are not 2 people who flip heads, and there's 1 way for 0 people to flip heads. They all just flip tails. 1 head is essentially the same thing, but 8 people. And there are 8 people who could have flipped the heads. 2 heads is the same thing, except we have to subtract the 8 cases where they're next to each other. So 8 pick 2 minus 8 is equal to 20 cases here. Okay, 3 heads is a little complicated. So so let's consider the ways that we can have 3 heads. So firstly, there are 8 ways to choose one of the people who flipped heads, and then in successful cases, these 2 people couldn't have flipped heads. And now, we now count how many ways there are for the 2 remaining people to have not touched in this 5 people. So the number of ways to choose 2 people who flipped heads is 5 pick 2, but we have to subtract the 4 ways that the 2 could have touched. So 5 pick 2 minus 4. And then notice we have to divide this whole expression by 3, because picking this to be heads and then picking this and this is the same as picking this to be heads and then this and this, or picking this to be heads and picking this and this. We overcount by a factor of 3. So simplifying this, I think that we get 16. And 4 heads, pretty easy to see. The only way this can happen is a heads, tail, heads, tail, heads, tail, heads, tail arrangement. It's like the beekeeper problem. So the only ways this can happen are these 4 are heads or the other 4 are heads. So that's just 2. So we have to add 1, 8, 20, 16, and 2. So it adds up to 29 plus 18, which is 47. So our answer is A. Problem 5. A rectangle is partitioned into 5 regions as shown. Each region is painted a solid color: red, orange, yellow, blue, or green. Let's just use A, B, C, D, and E for the colors, because it's annoying to just use the initial letters. So that regions that touch are painted different colors, and colors can be used more than once. How many different colorings are possible? So this problem is pretty simple. So there are 5 ways to choose the color of this region. Let's just suppose that its color is, for example, A. So 5 times. And then there are 4 ways to choose the color of this region down here because it can't be A. So let's just say it's C 4 times. And then there are 3 ways to choose the color of this region because it can't be A or C. Let's suppose it's D 3 times. There are also 3 regions to choose this region up here because it can't be A 3 times. Suppose it's E. And lastly, there are 3 ways to choose the last region because it can't be D or E. For example, we can let it be A, B. And this is equal to 540. And lastly is problem 6. A player chooses one of the numbers from 1 to 4. After the choice has been made, 2 regular 4-sided dice are rolled tetrahedral with the sides of the dice numbered 1 through 4. You can assume that's they're fair. If the number chosen appears on the bottom of exactly 1 die after it has been rolled, the player wins $1. If it appears on the bottom of both dice, then it wins $2. If it doesn't appear on the bottom of either dice, the player loses $1. What's the expected return to the player in dollars for 1 roll of the dice? So we're going to look at the probability of each case. The probability of it landing on exactly 1 of the dice. Let's just assume that they choose 4 for simplicity. All the numbers are the same, so we can just assume they chose 4. So these are the 6 cases in which they could have gotten exactly 1, 4, 1, 4, 2, 4, 3, 3, 4, 2, 4, and 1, 4. So that's a total of 6 over 16 times the return of 1. Plus, and then there's only 1 case where it lands on 2. So 1 over 16 times the return of 2. And then plus a 9/16 chance, there's 9 remaining spots of them getting -1. So this is equal to 6 over 16 plus 2 over 16 minus 9 over 16, which equals to -1 over 16. So our answer is B. Okay.